All right, the rest of today is about enthalpy of reaction. So again, set of notes for you in Schoology. Please go ahead and use those or take your own as always. Right, so earlier in the year, we learned what enthalpy is, right? Enthalpy is a measure of the internal energy in a particular reactant, plus any energy that it's exerting as a result of pressure or volume work that it's doing. Now remember that enthalpy is very hard for us to actually measure, but we can measure changes in the enthalpy because in a constant pressure situation, it's basically just the heat that's created in a change, right? Either created or heat that's absorbed in a change. So we're going to recall the change in enthalpy, delta H, is the enthalpy of the products minus the enthalpy of the reactants if we're talking about a chemical reaction. So delta H is the enthalpy of the products minus the enthalpy of the reactants. That quantity, delta H, is called the enthalpy of reaction or the heat of reaction. It's the difference between the energy of our products minus the energy of our reactants. Or in other words, the heat that's given off by a reaction or the heat that's absorbed by a reaction. Okay, so again, enthalpy of the reaction or heat of the reaction is just the enthalpy change that occurs or the heat change that occurs in a chemical reaction. So because it's a measurable quantity about our chemical reaction, we can actually use it within our chemical equations and in other situations to understand more about the energy changes that occur within a chemical reaction. So a couple things that we need to understand about the enthalpy of a particular reaction. First of all, it's proportional to the amount of reactants consumed in the process. So basically, in other words, if we have twice as much chemical involved in the reaction, we're going to get twice as much heat out of it. Okay, so the implications of this is that we can stoich it. Okay, if we know the certain amount of the reactants, we can figure out how much energy needs to be added or how much energy is released in the process. Okay. We can also write it into a chemical reaction equation. Okay, if the enthalpy is positive, in other words, if it's endothermic, that means energy is a reactant because we have to put it into the chemical reaction. If enthalpy is negative, that means energy is a product. Energy gets released by the reaction, and so it's exothermic. Secondly, the second thing we can know about this is for a reaction in the forward direction is equal in size but opposite in sign to the delta H for a reverse direction reaction. We haven't talked a bunch about forward and reverse reactions, but you can reverse any reaction or many reactions just by adding or getting rid of energy involved. Okay, so if I wanted to go through combustion of methane to carbon dioxide and water, that would be an exothermic reaction that would release 890 kilojoules of energy per mole. Okay, if I wanted to take carbon dioxide and turn it into water and turn them into methane and oxygen, that is a reaction that's going to require 890 kilojoules per mole of energy being put in. Okay, so again, same reaction in opposite directions gives us the same delta H, but in opposite sign. The third thing to know about enthalpy of reaction is delta H for a reaction depends upon the state of the products and the state of the reactants. So in other words, if we were going to make water in the gaseous state as a product of combusting methane, that's going to have a different enthalpy than making water in the liquid state. In a liquid state, we would get a delta H of negative 802 kilojoules, whereas making a water vapor would give us negative 890 kilojoules. Okay, so again, we have to pay attention to states when we're doing calculations relating to enthalpy. And last but not least, delta H is reported per mole of reaction. Okay, and so what does that mean? Well, one way of thinking about it is every time you run a reaction through, you've done a mole of that reaction. And so then the coefficients in front of the products and reactants that are part of that are multiple moles of reaction. We'll get a little bit more into how this works in just a second. But the reason why this is important is because the unit used in AP chemistry is kilojoules per mole reaction. So this means when we're calculating the delta H for a reaction, we need to divide by the number of moles of whichever chemical we use to determine the delta H. Okay? And the reason why we do this is because that will eliminate different values depending upon which chemical is used to calculate the delta H, because it will show up as different numbers of moles would give you a different number if you didn't standardize it all to kilojoules of mole reaction. This will make more sense once we do an example, which is next. All right, so in the lab, you make 1.5 moles of substance C in the reaction. A plus 2B goes to 3C. The reaction gives off 667 kilojoules of heat. Calculate the delta H for the reaction. And we're going to want to report this as kilojoules per mole reaction. All right? So how does this work? Well, 1 mole of substance A is going to be what is used up in 1 mole reaction. 2 moles of substance B are going to be what's used up in 1 mole of reaction. And 3 moles of substance C is what's going to be used up in 1 mole of reaction for this particular reaction based on that. Okay, so the number of moles of the substance, coefficients, are going to equal 1 mole of reaction as a conversion factor. All right, so in the lab, we make 1.5 moles of substance C, okay? And it gives off 667 kilojoules of heat. And we want to turn this into kilojoules per mole reaction. So I can start off by going 667 kilojoules of heat per 1.5 moles of substance C, okay? But we don't want kilojoules per mole of C. We want kilojoules of per mole reaction. So I'm going to use my equation up here, and that's 3 moles of C per 1 mole of reaction. The moles of C cancel, and so this gives me a calculation of 1,334 kilojoules per mole reaction. Okay? All right, so, which is very different than the amount of kilojoules per mole of C, which would have been 667 divided by 1.5. And again, the reason why we do this is, imagine that we had looked at how much A was used up, okay? Well, we get 1.5 moles of substance C at a 3-to-1 ratio, so that means that we would have actually only needed to use 0.5 moles of A in order to get 1.5 moles of C. Well, if I do that, 667 kilojoules per 0.5 moles of A, the ratio is 1-to-1 for moles of A to mole reaction. 0.667 divided by 0.5 gives me the same value. Whereas, if I had just figured out for moles of A, I would have gotten 1334 kilojoules per mole, or per A, whereas I would have gotten a much smaller value for kilojoules per mole of C. Okay, so again, mole reaction makes that all equal out. This only applies, again, if they're asking you to calculate the value of delta H. If they just want to simply know how much heat is created, you don't need to worry about mole reaction.